Okay, I guess we can start then with the first talk is by Moritz Kiehn, which is about similarity hashing in the HL-LHC ATLAS detector. So I'm happy for you to open this conference for us. So please go ahead. You have 15 minutes.
Thank you. So as mentioned, I'll be talking about hashing similarity learning for tracking, also with the ATLAS detector. So first of all, why should we consider new tracking techniques? Tracking is at the core of almost every particle physics experiment. And in the high luminosity area, that means PILAB 200. And traditional combinatorial approaches are exploding exponentially. And so you can cope you can cope with that a bit by increasing cuts. But if you have better algorithms available, you could do better physics. And so that's a reasonable thing to try to look at tracking from maybe a slightly different point of view. What do we mean with hashing? So you might know what a typical hash function does. You have a complex object, apply the hash function, gives you a number. This you can then use in hash maps, for example, Python dictionaries, C++ unordered maps, to do fast lookup of complex objects in constant time. How would that look for tracking? So ideally, if that would exist, you would want a perfect tracking hash function where essentially you compute the hash function for a given hit and it directly gives you a track number. Unfortunately, of course, that does not exist because hits don't have track identity. But the idea is that we could maybe do something a bit more approximate, where instead of perfectly assigning them, if we could just group hits together reasonably enough so that hits from the same track always end up in the same group, then we can already construct a data structure where we can do really fast lookup for hits within the same track and do tracking that way. The question is, how could we construct such a hashing or such a hash function? One way to do that, for example, is what's called random projections, where you take the items that you want to hash, so in our case hits or any n-dimensional objects essentially, with a given metric, and you generate a random division within the distribution within your items, and then things on the left get 1 bit 0, things on the right get another bit 1. And by doing many of these random projections, you can build up a hash for that. And if you do that multiple times, the idea is that things that are close together within that space end up always with the same hash function. And so you can use that to group similar items for a given metric together into what's usually called a bucket. So that means you can query, if for a given item that you have, you can query which bucket it is and then get neighbors, thus build tracks. So this is not the only thing that you can do. There's in general, these type of problems go by the name of approximate nearest neighbors searches. And there are actually quite a few number of methods available, used by quite a few well-known companies for various purposes. And we actually ended up for our studies using a library called Annoy from Spotify. So we're using their library directly to do these kind of studies. So how does that then look like? Or what's the general approach that we take? We start from the hits that we get for any kind of event. We then build the approximate nearest neighbor data structure for these hits. This is a one-time cost that you pay for each event. And then you can take a hit and query for its neighbors. And by this, you create buckets. And with this buckets, you essentially are subdividing your problem space into smaller, significantly smaller regions. And by doing that many, many times, you can find all probable or all reasonable buckets for which you do tracking in. And then within the bucket, now you only have a limited number of hits, 20 to 50 typically, you can then do local reconstruction to finally actually reconstruct the tracks, assuming that within 20 or 50 hits, we can do that. So how well does that work? So this is a plot of the tracking efficiency. For one example here, the data that we were taking was from the TrackML dataset, which is a TT bar collision sample with a pileup of 200 with a semi-realistic detector around it. And you select the buckets using randomly drawn hits. So you pick a random hit from the available hits and look for its neighbors. And then you define the efficiency by counting how many trackable particles in the buckets that you've seen so far exists over the total number of trackable particles. And by trackable, we mean here particles above 1 GeV and which have at least 4 hits, because, for example, from Atlas, we know that if you have a seed with 4 hits, you can complete it almost all the time. And as you see, as you increase the number of queries, you start to get reasonably high efficiency already after a few thousand queries. And for example, you can also see if you make your buckets larger, then statistically you have more chance to pick up the right hits. This all was probable data structure. Also, and so if you go from 20 to 50, you can do more hits, of course, at the expense of noise. So that means the basic idea works fine and well. What could we possibly improve for that? So we're essentially looking for neighboring hits. And so the neighborhood or neighborhood in this case means hits from the same track. So the neighborhood definition depends on a metric. And so far the default distance is the angular distance. But what you actually want to have is you want to have a metric where you optimize the separability of hits from different tracks. So here is, and this procedure goes by the name of metric learning. And here you see an artificial example where on the left you have the initial space where you have the different colored coded groups interleaved in that space, and by applying an appropriate transformation, you can then into a learned space. You can then much better separate that. So if you have a better metric, that means you can better separate, you have better buckets, you have better tracking. The question is, does that actually work for the data that we have? This is an example where on the left you see a particular cutout from a few set of tracks in the XY plane, only the hits. You can see where there might be probable trajectories to interconnect them, but they are spatially closed. And then using an algorithm based on local Fisher discriminant analysis, we've learned a transformation into a separate space where here the now color-coded groups of hits belonging to the same track are actually well separated. I have to say, this is, I have to add a caveat here. This is uses the TrackML dataset with additional hitch features, which are not easily available or not easily translatable in other cases. You can actually do it, think about it the other way around. So if you have a better detector, you can actually do much more things with it than just space point tracking. So that's why this was not easily translated, for example, for the Atlas cases. So the method in principle works. We've seen that. How fast can we make this? And one of the questions nowadays is always, can we run this on an accelerator, a GPU, or an FPGA? And if you think about it, this approximate nearest neighbor choice is the very general problem. You can not only search for similar hits, you can search for similar images, movies, or people. And obviously other companies are interested in that. And there's, for example, a paper here from Facebook where they were doing a billion scale similarity search based on GPUs, actually on using a slightly different technique from the one that I showed at the beginning. So the idea is, could we just try that out for our example? And actually, yes, we can. So this is the same data set as before. What's shown here is the distribution of the leading particle size within the reconstructed bucket. And you see that both the GPU and the CPU implementation of the same algorithm with the same input data gives you consistent results. So you can actually just switch out the implementations and see how fast that actually goes. And this is shown on the next slide, where we show again a plot of the efficiency. This is the black curve as a function of the number of queries that we perform, so how many buckets we reconstruct. And you see again that after a few thousand queries, we get reasonable efficiency or good enough efficiency. And you also can see on the left, the red plot is the time it takes. So now we only need a few milliseconds to query the data structure for all the hits. And in addition, all these queries are fully parallelizable. So they are independent from each other, and you can take full advantage of the available parallel computing power that you have. So now this is the case. This was all done on TrackML data, so on a bit optimistic case. So we want to apply how this actually works in a real detector. And the use case that we're most interested in at the moment is the ATLAS ITK upgrade detector. So here again, we take a similar data set, a TT bar event with a pileup of 200. We use the initial method that we just mentioned, the Spotify library, to select buckets of hits. And then we apply the Atlas reconstruction within each bucket. So the idea is that this is not necessarily what you would want to do at the end. It is considered more of a proxy for future local reconstruction. But this is the reconstruction that we have at the time. So to be able to compare, once you do this pre-selection, how well can you reconstruct within that, and if you're missing anything, or if there's something that might not work as intended. And so then to compare, what we do is we reconstruct the same event once with the full Atlas reconstruction software. We get a set of tracks. And then for the other case, we split the event. We generate from each event 5,000 bucket using the methods that we described above. Then we run the reconstruction, the Atlas reconstruction for each bucket. And then we see, then we get a list of tracks for each of the buckets, can merge them again. And then afterwards, we can actually compare apples to apples, how well we reconstructed each track. This is an example for one of those simulation events. You can see the color-coded dots at the bottom. For example, these are the hits in the bucket, or there's a yellow one on the back on the top right, and then this particular bucket would have two underlying particles within. So it's an effective pre-selection. And with that, you can then compare the two cases. And what's plotted here is the size of the reconstructed track on the bottom for tracks that match, so that were reconstructed both in the buckets and in the cluster case. On the bottom is the track size in full events. On the left side is the track size in the bucket reconstruction. So on the diagonal, what you see are tracks that are fully matched between the two. So they are reconstructed exactly the same and are fully contained within a bucket. And then below, what you see, the entries below are particles where you are missing hits within the bucket. The majority of these cases is from low PT tracks or lower PT tracks, where the bucket does not contain all the hits that exist for that particular track. But these can be easily recovered if, once you do the tracking, you can extend the bucket or allow the full reconstruction to include additional hits. And then above, you actually have cases where within the bucket there are a few more hits included that are not included in the general reconstruction case. So to summarize this, I've shown you how to do tracking via approximate nearest neighbor methods, particular hashing and similarity learning. This is a general detector independent technique. It's unsupervised, so it doesn't depend on any particular knowledge that you need. And it shows quite promising results on TrackML and Atlas ATK datasets. And we're currently working on getting this towards really a full reconstruction chain. So finally, we can do a comparison of everything to everything else. And with that, I want to close and thank you all for listening.
Thank you, Moritz. We have time for 1 or 2 questions, I think. I'm waiting for people to raise their hand. So far, I've not seen anyone. Okay, Salvador, please go ahead.
Okay, thanks. Well, thanks for the talk. I found it quite illustrative. The only thing, I mean, you were really very fast when when going back to page number 6. Okay, so you defined the problem very well. So the introduction was quite nice. But okay, you have. I mean, for me, it was not very clear. I mean, here it was a very big step here. How you really move from hits to buckets. I mean, how you really classify. I mean, which is it? I mean, these methods that you are quoting here, how they really work on the hits. I mean, what they are checking what the each are close. How you measure the metric.
In general, what all these methods do is they take high dimensional objects, and given an input object like that, they search for a fixed number of items within the collection that are as close as possible, or approximately as close as possible. So in our case, the closeness is defined by a metric. In our case, this is an angular distance, essentially opens up a cone-like structure. But it's not a fixed size cone because the actual subdivision depends on the density of the data that you have within each event. So it's not as simple as doing just a cone search in this case. But in general, the idea of these approximate nearest neighbor searches is you have a set of vectors, in our case, the hits, which are 2, 3 dimensional. If you include additional properties of the hits, you can make it higher dimensional and then search for ones that are close within that metric.
Okay, but then it's just, let's say, an angular distance. Okay, a tune angular distance, right?
It's
okay, yeah, okay, I see. All right, thanks.
Any other urgent question? That does not seem to be the case. So thanks again, Moritz, for this talk. And I think then we can go on with Louis.
Can you hear me?
I can hear you fine, yes.